I'm going to present a collaborative work between the universities of Huddersfield and Bristol in the UK, made possible within the so-called Sphere project, which is headed by Bristol and also includes Reading, Southampton, and some other UK universities. So the topic here is mainly healthcare. So using homes that are being equipped with sensors in order to address several healthcare-related goals. And in that context, what we're doing is trying to realize activity recognition using a rule-based expert system. So, I'm going to talk about some general stuff. What is activity recognition and how it fits within the Internet of Things paradigm. Then some things about the Sphere project and how it was used to influence this work. What has been done before in the context of logic-based activity recognition. And then I'm going to focus on the system that was developed and some results that we have and some concluding remarks at the end. So, this work is influenced by the general revolution that has taken place nowadays with sensors becoming cheaper, smaller, and widely available, giving us a wealth of information available to be used to extract even more knowledge information, and especially when you have an Internet of Things setting which allows you to have benefits such as distributed resources, common access strategies, ontologies to describe the same kind of knowledge with a common way, and of course availability of computational resources. So in these cases you not only have information available, but you have more easy access to it. And in such a context, we can do more stuff than use single sensors in order to extract simple knowledge, such as, for example, the fire alarm goes on, so there's a fire. We can actually fuse the available information from disparate and multimodal sensors in order to extract actual activities that have been performed in a sensor-based environment. Now, the challenge in this case, you have the information, you need to know which parts of this you are going to take advantage of, and how to fuse them in order to extract the knowledge you want to extract of. Now, to realize sensor-based AR, so AR that is realized based on data collected by sensors, there have been two general families of works that have attempted to realize it. So, on the one hand, you have machine learning, which excels at handling noise and uncertain cases, but of course it relies on training most of the time, and data conflicts are not strongest hand. On the other hand, we have logic-based approaches where you have the benefit of not requiring training, but then again there are less robust against noise, and of course, especially in our case, in order for them to work, you need some kind of expert to carefully create the rules behind the system. So, this is a general setting for activity recognition. Now, if we try to focus on a specific use case, namely the smart home environment, then first of all, we're not looking for any kind of activity to be recognized. We're focusing on a subset of them, usually called activities of daily living, and then our goals are more specific. They address efforts to assist the elderly, assist people requiring help at homes or in other facilities within the context of ambient assisted living. And it might also be not only direct assistance, but also have a long-term monitoring process of the actual life of the person within the smart home in order to derive information related to these people. For example, Parkinson or Alzheimer's cases can be detected if you have a long-term monitoring of a person's behavior. So in that context, in that specific subset of the whole activity recognition area, we found that there are a set of requirements that are more important than others. First of all, when you have multiple sensors, it becomes more and more important to be robust against noise rather than having simple sets of sensors. Then, since this is an actual home where people live in, you cannot rely on specific sequential scenarios of life. People do what they want to do in their home, in their own order, without any limitations to it. Also, in a smart home, it is important to not only know what the user does, but where he or she is located within the house, and without actually bothering the user with it, making it as seamless as possible. And then, what also is required is to have this extraction of knowledge, not only in an offline mode, collecting data and then deriving information out of it, but also have it done in real time as soon as the sensor events have been captured. And a final requirement, which gives more likelihood to use a rule-based approach rather than a machine learning one, is the difficulty of collecting training data in such environments. When you have smart homes, each smart home has its own setup, its own design. People living within it have their own differences, and then you have to collect training data again and again and again when you move from one home to another. So this makes it a bit more difficult to rely on this training data. Now, in the case of the Sphere project, what is the impetus of this project was to create a sensor platform combining different sensor modalities in the same system, deploy the system initially in a test bed called the Sphere House, and see how things work, collect information, and try to do stuff with it. And then eventually, at the final stages of the project, which are beginning right now, deploy the final version of this system within Bristol in the UK in 100 homes selected through a process of acquiring participants that are interested in such technologies, and actually apply this system in real-life situations, with the purpose of addressing any healthcare need that can benefit from long-term monitoring of behavior. Now, in the context of using logic-based approaches to realize activity recognition, there have been some works here. In all cases, you have some benefits, you have some deficiencies. For example, the well-known work of Chen et al. Uses equivalence and substitution reasoning to realize activity recognition. It models both the sensor data and the actual activities to be derived through an ontology. It actually supports both offline and real-time modes. It can recognize incrementally specific activities, but it only works when the activities are performed following a specific scenario with a sequential order and with fixed time intervals. And then you have MetaQ, which represents data using RDF, uses Sparkle in order to realize activity recognition. It also has a gradual way of building activities from smaller ones to more complex ones, but it doesn't have a real-time mode, nor does it support activities that are missing from the basic description. And then there have been works that try to bridge the gap between the rule-based way and the machine learning way, the so-called hybrids. For example, this work from Scarlatidis uses event calculus reasoning, but in combination with Markov logic networks, and this allows them to achieve high recognition rates and, of course, benefit from robustness against missing data. But their use case is only restricted on specific simple activities related to posture and movement, as opposed to complex scenarios. And then the other case of a hybrid, the Helawi one, uses a probabilistic DL reasoner. This supports complex cases, but requires training data. It doesn't work in real time, and there is no support for temporal features, the time stamps at which each activity is performed. So, in general, what we see is that while some approaches achieve one subset of the requirements that we discussed, they unfortunately do not support the rest. So, in this case, we set out to create a rule-based system, a rule-based expert system, to address all of the aforementioned requirements. Now, it follows the typical design of an expert system. A rule-based was constructed by examining collected data from the Sphere house, from the actual deployed sensor testbed. We created these rules based on the data, and then we populated the fact base from these exact data. Now, as I mentioned before, we have two modes. In one case, all data from the experiments are stored as individual facts, and then the recognition process tries to reconstruct the narrative of the activities performed in the house for past periods. Now, in the other case, in the real-time case, there are facts in the fact base representing each node in the house and storing its current state and its previous one. And this allows the system to recognize an activity at the moment in which all the associated sensors report their values. Now, as far as sensors are concerned, we focus on environmental and video sensors. We excluded the third modality included in the Sphere project for now. Now we have door contact sensors, electricity meters, water flow meters, passive infrared sensors. There are some other sensors included in the testbed, but they haven't been actually so useful in creating the rules. For example, the light sensors that are deployed in the house proved useful only in the cases when the outside sunlight was minimal. In other cases, the change in sunlight wasn't enough to detect activities such as turning on and off a light. And in the case of video sensors, we exploited both the 2D bounding box coordinates, which surround the person being located in the house, and the depth coordinates in order to know the distance of the person from the camera. Now the rule base looks like this. There are two groups of rules at the lowest level. You have rules that have to do with simple activities, interacting with doors, devices, opening and closing tabs, and so on. And then you have rules that have to do with the location of the user in the house, exploiting both infrared sensors and the video cameras deployed in the house. And then you have an intermediate level where a single location for the user is decided based on the available knowledge. And then on higher levels, what happens is I combine the knowledge from the atomic activities that I know have happened and the location of the user at the house to decide on more and more complex activities that have occurred in the scenario. The important limitation here is that we assume that there is only one user at home at any given time. And this is one of the topics for future work to lift this limitation. Now, some examples for the lowest level rules. For example, a change in sensor values from positive to zero values or the opposite means that the door has opened or a device, the associated device, has been switched on or off. And this is the way the rules look like in pseudocode. And then in the case of water taps, and of course, what I didn't mention, each sensor has its own reporting window, which has to be used when defining the rules in order to decide on these events. In the case of water taps, you don't have a reporting period, but as soon as the user uses a tap, opens or closes it, there is a value reported which corresponds to the actual flow. So that's what the rules exploit. And in the case of taps, since each time a positive value is posted, then an OpenTap event is recognized, then there needs to be an intermediate mode where you clean up all these redundant OpenTap or closed-tap events and keep only the earliest one in time. And then after having recognized these simple low-level activities that are closest to the sensor infrastructure, then you try to combine them, defining rules that try to extract information about more complex activities. And some examples here are a set of low-level activities of choosing on and off a device means that the user is using the device. If the device is the TV, then the activity is watching TV. And then you can combine, for example, use of taps in the kitchen, using the fridge, to derive cases where you say that the user is preparing a drink or a snack. And then you go another level higher, and you use a second level activity in combination with a first or second level activity to derive yet another one, and you go on and on, building up, trying to reconstruct the actual scenario that happened in the house using such rules. Now, these rules may have choices where you may derive an activity by different combinations of activities. You may also have cases where an activity is optional. It doesn't have to take place in order for another activity to be recognized, and so on.
On that side of it, T1 and T2 are timed, yeah?
Yep.
What if you turn off the TV, the time T2, and then turn it on again at time T1? And it's not being used in between.
Yes, so you essentially have pairs. You have one timestamp when somebody turned it on, and one timestamp where somebody turned it off. And this is a pair which gives you a watching TV. Then the next time you open it up, you have a new switch on activity at T3.
Yeah, but how do you know the T2 comes after T1?
Because these
are
are
other incidents of turning off.
Because these are the actual timestamps. So T1 is always less than T2, so it comes before in the timeline.
But you can turn it off and on several times.
So each pair of these turning off and off on will derive a single watching TV fact, and then the next pair of turning off and on will give you the next one, and so on. That's the way you reconstruct the cases. So you have 4 or 5 times of turning off and on, you will have 4 or 5 cases of watching TV for these specific intervals.
I guess I don't see where T1 and T2 come from. Maybe this.
So do you use a sequential end? T1 is automatically before T2 because it's a non-symmetric end. Or is your end your conjunction symmetric?
Oh. I mean, these T1s and T2s are specific time values extracted from the sensors. So when a sensor posts a value, it posts an accompanying timestamp. So there's no disambiguity there.
I think the problem is simply you didn't add like a T1 is smaller than.
Oh, it's always there. Yes. You see here all rules.
Oh yeah, there you go.
Yeah. But here I'm only showing the combination. Yes, all rules. What happens is that all rules have explicit time-related temporal features within them, and that's why I was talking about reporting periods, because you need to not look at the whole timeline, but only on the specific periods that the sensors report. Okay. Now, as far as localization is concerned, which is equally important to discovering the activities performed in the house, we use 2 sources, the infrared sensors and the video sensors. Now, in the case of the infrared sensor, each pair of activation and deactivation equals to a sequence in time where the user was in the room. In the case of the video, you don't have an activation or deactivation. You actually have a bounding box being reported, so a set of coordinates being given by the camera. Now, the special case within this project was that Sphere wanted to keep the cost of the sensor platform low, so the video cameras they used were simple Kinect-like devices, which unfortunately have a serious problem of detecting ghosts. So they're really sensitive, and they always report that one or more persons are in the room when nobody is there or only one is there. So there was a great need of trying to clean up this data, and we again used rules for this. We tried to define some heuristics which say when a specific bounding box sequence corresponds to an actual person or it's actually a side effect of the camera. So some cases are these when the camera reports for less than basically a second, when the camera bounding box is stuck in the specific same coordinates, which means that there is no movement at all. Of course, if actually the user is sleeping, then we have a way to bounce back from this and actually not lose this knowledge. Also, if the width and the height of the bounding box is unjustifiably small, if we take also in consideration the depth, so you have a really tiny bounding box, but then also the depth is really small, so how can this be? So in such cases, we clean up the knowledge and try to keep only the actual cases where the camera detected the person. Now, these two sources are then fused, the infrared localization and the camera localization. We assign some confidence values to these sources. In the case of PAR, if more than one infrared sensors report a location, then confidence lowers. In the case of video, if you have simultaneous, if you have a sequence and all of these conditions hold, then it's highly likely that it's a ghost and not a real sequence. And then, for each case, we combine them in order to extract a single decision. The user is in this room and this room only, using these 5 different cases for deciding it. Now, in the case of real time, the basic thing that changes is the nature of the fact set, as I said before. Instead of having a fact represented each sensor value, you have a fact represented its sensor state. So this keeps the fact base at a really small footprint, which allows the system to operate equally well in real time. Now, the fact that the rules are built from the bottom up means that changing the fact base, which collects the sensor data, leads to a change in the lowest level of rules only. So the rules that act directly on the fact base, directly on the sensors, are the ones that needed to be modified to work in real time. And essentially the rules take each change of state for its sensor and link it to a specific related atomic activity. And the benefit of this is that those cleanup rules that were mentioned before in the offline case are no longer necessary, because rules fire only at the point in time where the sensor state changes and not any other time. Now, localization in the online case is similar, but instead of having a history of data to derive activations and deactivations of PAR, we have a narrative which begins the moment the system turns on. Each time we have a set of activation and deactivations, we assume the user is in the room. If we have a follow-up activation, we either extend the current user stay, or if the time distance is different, if the user has been detected in a different room, and so on, we decide when to say, okay, this user stay is different than the next user stay in this room. And in the case of video, we couldn't apply the state-based approach because this sensor doesn't report a single value. You have actually 8 different values reported, so you would need to keep before and after values for all of them. So instead, we simulated the offline case. We store the bounding boxes briefly, only to combine them to create facts at a slightly higher level, representing the period of stay of the user in the room. And ghost detection is essentially the same case. You search for the same patterns that characterize a ghost rather than a real user. And in the case of fusion, we follow a different path in the online case. Each time we have an activation from an infrared sensor, we check its validity using available information. So if a camera reports something different, then we are not sure that the PIR sensor actually reported the correct location. So we then use different information, for example, an activity that has been detected in a room, and we fuse all of this knowledge in order to decide which source says the truth. Is it the PIR sensor because an activity actually happened where the PIR sensor detected the person, or it's not? So all of these rules in both the offline and real-time case were implemented. We used JES as a rule engine and Java as an implementation language. What needed to change from the theoretical rules to the actual implementation is that in the real world, reporting periods are not actually kept to the letter. Sensors tend to report whenever they want or whenever the system works as it should. So they had to accommodate variable reporting periods to not miss actual events happening. In the real-time case, we built the system as an MQTT client to benefit from the actual sensor infrastructure in the Sphere house. We use multi-threading in order to make sure that we do not miss any sensor broadcast while processing a previous one. Then we collected data within the Sphere house. Basically, 10 people stayed in the house for a short period, for half-hour durations each time. They executed a script containing a set of activities of daily living. They had a camera attached to a head-mounted camera, which collected the ground truth, knowing the exact activities they performed. And the implemented system can recognize a subset of the activities within this scenario, basically interaction with doors, electrical devices, and water taps, preparing a snack or a drink, washing hands or dishes, brushing teeth, and bathing or showering. Now, for all of these 10 experiments, we evaluated them. We used the typical information retrieval notions. In our case, a true positive means that an actual performed activity has been recognized. A false positive, the system recognized an activity that actually didn't happen. And a false negative, we neglected to recognize a performed activity. Now, we evaluated both the actual recognition accuracy and the case of localization. Now, in the case of localization, the numbers are simply the percentage of time that the system reports the correct location of the user. And you see here that we managed to move forward from the deficiencies of the sensors, the cheap video sensors, and have an average of 92% accuracy in localization, basically because each sensor validates the other one, cross-validation of sensors. So in general, the resulting system can work in two modes, both relying on historical data or actually extract actual activities at the moment they are sensed by the sensors. There is a bottom-up multi-level system of rules designed to derive more and more complex activities from the sensors. These rules can account for non-deterministic cases with or without some activities. And the results are good, but we should keep in mind that they're only for single residential scenarios, only one person in the house, and also for a subset, a significant one, but a subset nonetheless of the activities performed. So what we're doing now is we're trying to integrate the third modality of sensors in the Sphere project. Apart from environment and video sensors, there is also a wearable, a wrist-worn wearable that is used to collect data. And this may help us identify activities that we couldn't with only the other sensors. And also, it can provide an alternative for localization in cases where either we don't have cameras in rooms where cameras are not allowed, or in cases where users have opted out of cameras, which is actually the situation right now. You have users who decide not to have cameras deployed in their house. Now, the other interesting case is multi-inhabitant scenarios. In this case, localization plays an even more important role than in the single case. You use the location of the user to pin down activities to the actual person performing them. And in such cases, you also not only need to know where the user is in a room level accuracy, but a bit more fine-grained in order to understand when you have two people in a room, which person does which activity based on the position in the room that they are. And the third direction for future work is to try the hybrid case. So there is a team within the Sphere project that works on machine learning, trying to do activity recognition using machine learning techniques. And we have begun discussions on how to integrate these two directions. One of three ways. The first one has already happened. The rules are used as features in their algorithms so that they do not act on the raw sensor data, but rather on the inference that we have created with the rules. The opposite case could also be possible, and especially in the case of wearables. The rules cannot easily act on data as complex as wearable sensor data, so maybe it's better for the machine learning system to do a first work on the raw data, and the rules will act on the first level of knowledge gathered by the machine learning system, and also find a way within machine learning to make the system learn the rules that we have expressed here. And that is all. Thank you for listening.
Yes, I have a question. Embedded systems with sensor regularly exhibit clock skew. So over one day it's negligible, but over like a month, 6 months, and a year, it starts becoming significant.
Yeah.
Do you account for that?
And it's actually, yes, it's actually one of the things that we're doing right now, because the Sphere project has moved from simple half-hour experiments to weekend stays in the room, and this has actually become a problem. Before it wasn't noticeable, but right now it is, and it is one of the things that we need to look for, this clock skew. And also the fact that, not only that, that some sensors have their own clock and they do not agree with the clock of some other sensors, which is even worse, because, for example, in this system, this relies on combining knowledge from different sensors. If these timestamps are different, then I will derive wrong knowledge, yes. So this is absolutely a thing to look for.
Good luck with that.
I have a number of questions, and maybe we can take that offline. I was interested in your offline mode. You said when you go from offline to online, you no longer need this history of thing.
Yes.
History of sensor events, but even in online mode, it's useful to have a history of sensor events. No, and like you said, if the user's determined to be in a room, then for like a few seconds he's not, and then he's again in the room, like for some sensor glitch or whatnot, you need a history of events as well. No?
Yeah, you keep the history of the derived, so that's what I'm doing. I don't know if it's correct. I discard the actual raw sensor data and only keep the lowest level of sensor events derived. So I will keep the fact that the user was in the room, but I will have discarded the actual numbers of the sensors that were here. So I keep the knowledge, but only at the one step above from the raw one.
Guessing you also need to use some sort of window, not to keep it like a week or two.
Yes, of course, but these experiments for now are really limited, half-hour ones. So.
That's fair. Also, so you detect ADL activity. I think you were present at my talk where we actually focus on acting upon an assisting with ADL. It's nicely complementary. That's certainly not a thing.
Yeah, and actually, I mean.
So my question is actually, what do you do then once you detect them? What's your action plan there?
The thing with Sphere is that it was designed not for direct assistance, not for the things that you are doing, which are, in my opinion, far more important, but for long-term monitoring. So their use case, I don't know how exactly it began because I wasn't in the starting stages of the project. Their use case was diseases like Alzheimer's or Parkinson's, which have a slow degeneration of the human body. So you monitor a person for years rather than days, and use this monitor information to say, okay,
see what the progress is.
exactly. So answer the question: can we really realize that the person is afflicted even before current methods can do that? But that's the use case they have. So no direct assistance within the
The
spirit.
thing is, I mean, typically you would only move people to a smart environment and like an assisted living environment once you know that they're in trouble, right? Once you know that they're somehow.
The idea in Sphere is to make people participate in this process, not as afflicted patients, but actual healthy people who. So that's what happens right now. There's a project called a side project called Friends of Sphere, where people from Sphere gather around the city in Bristol and accept people, explain the whole project to them, and 100 cases of them will eventually accept the sensors to be deployed in their houses, not because they have Parkinson's or have Alzheimer's, but because the use case is like that. What if you have a healthy person, you monitor them for years, and you can know beforehand that they are eventually going to have Parkinson's or Alzheimer's, something like that.
That's the use case. Okay.
Yeah.
Thank you.
A bit more technical question. I think one slide you used negation. I was wondering, because chess uses this production use negation, which is international negation. And if you have this asserted defect, that might lead to wrong results in the case of.
Yeah. It actually happens. So I try to limit the use of negation as much as possible. So mostly have rules that act upon the actual value of the sensor rather than something not being there. So in the current rule set, I didn't notice something like that, something that some problem derived from the use of negation. But I don't know if the rules become even more complex, if that will actually have an effect.
It's not a question on this, but an observation about the importance of these topics. Peer challenge. So interesting that we were able to organize the challenge at the conference just to. I'm the chair of this challenge.
Oh.
It's so interesting that the company gave us $10,000
Yeah.
prize for the winner.
It was, yeah.
Especially for the students, very interested. You can still apply for the
Yeah.
try to win
Yeah,
the prize, or at least attend the conference that is in Italy.
Yeah.
Next place.
To be honest, I was actually pleasantly surprised with this. They actually gave this Sphere data set. They opened it and they actually said, okay, people with machine learning skills, what can you do with this data? And this is
This is the reason why we talked
Exactly.
about,
and I'm really interested with the results that they're gonna get because
okay, so you have to wait 2 weeks more.
yeah.
So